Hi and welcome along to a video on young slits and superposition. Um, Sometimes I'll use the term superposition, sometimes I'll use the term interference or constructive interference, destructive interference. Anyway, without further ado, what are we trying to study this time? Well, got some pictures to show you. Let's start with that one, taken earlier today. So you can see the laser in the foreground a bit out of focus, and then you can see a kind of a black rectangle that's got two slits in it, and then you can see this is the pattern that I photographed on the wall. Neither of the photographs is perfect, but I'd like to notice at least two significant things in this pattern. One is that two slits has produced a very large number of bright spots, considerably more than two. You'll also notice that the dots get dimmer and brighter again, and that's something we might come back to in a future video. So how do we explain that? Well, it's all to do with superposition or interference. Now, I know some of you have seen this before, but it's, I think, really useful to have a bit of a reminder. So we've got two pulses on a string here. And now we have constructive superposition or constructive interference because they're both on the same side. Now we have destructive superposition or destructive interference. So the whole of that pattern is explained by the way that waves like these interfere or superpose. So let's have a look at that in another web simulation. Let's just start that. I suspect this will look fairly horrible in the video. We won't spend too long on this one. So what we've got here along the top here is two slits here and here. And then you can see 1, 2, 3, 4, 5, 6, 7 beams of waves coming out. So each one of those beams would form a bright spot in a pattern. So again, we've got the same effect, two slits, but producing many, many bright spots. So let's go to this one. I'm just going to stop that because it does use quite a lot of computer resources. Here we've got two sources. Again, let's just unclick that. They're not slits this time, although it doesn't really change the physics in any way. They're just kind of little things dipping in and out of a little pond. And in fact, let's just have a very brief look at the 3D view. It's a bit intimidating, but you can see we've got these two wave sources and we've got the waves spinning out. But again, we've got that distinctive pattern. We've got down the middle here, strong waves, and then we've got a line with no waves and then strong waves again. So we're not going to do any maths in this video. We're just trying to make sure that you can understand and explain how this pattern is being formed. And I thought the best way of doing that was to transfer over to Word, where hopefully I've got a picture that I've been working on earlier. Just got to get the right Word document. Right, okay. I was practicing drawing arrows earlier because nothing in the world is easy. I thought I'd be able to use my ruler like I do in the classroom. Oh, no, that's the wrong colour. I'd rather that was in red. And also I've got ink to shape on, right? So here in our pattern, we have a bright spot or a bright fringe. And what we've got to try and do is work out why is it all along this line coming down here, is it really bright? We get a bright fringe. Whereas all the way down where I'm drawing here, would it be dark? Why is there no wave activity along that line? And as I say, it's to do with superposition and interference. In fact, I'm going to... No. So what's special about this central bright point? Well, if we look at the two red arrows, which I drew earlier, and drawing arrows was remarkably difficult with this stylus, those 2 points are equidistant. They're the same distance from this bright fringe. So the waves that arrive at this point arrive in phase because they've travelled the same distance. And I think that can be a difficult idea. So what I'm just going to do is explain that using this thing that I've created here. So each one of these red double-headed arrows is half a wavelength long. We've got 2 identical trains of waves, which I can move around. But when they start at the same place, they remain in phase. If those 2 waves were to meet, then we would have constructive superposition or constructive interference. I think I'm going to use superposition from now on. And we would form a bright spot, or we'd form an area of significant wave activity. Now I'm just going to drag that to the right half a wavelength. Okay. Now you can see that the 2 waves are no longer in phase, are they? They're in anti-phase. They're completely out of phase, and the combined effect, if you added those 2 waves up, you would end up with no wave. And the key piece of terminology here is to say that we have a path wavelength, path difference of half a wavelength. The path difference means the difference in distance they've travelled. This one started half a wavelength further right, they're out of phase. But if I keep moving along and I make the path difference a whole wavelength, remember those red lines, double-headed arrows are half a wavelength long, we're now back in phase. We have constructive superposition, and therefore we would have a bright spot. We move another half wavelength. We now have a path difference of 1.5 wavelengths. That leads to destructive superposition because we're out of phase, and a dark spot, and so on. I'll just do one more. 2 wavelengths path difference. They're back in phase, and we get constructive interference. So let's go back to this picture here. I think it's getting a bit messy, so I'm just going to copy that out and put it into a new Word document. Right. Let's get back to explaining. I think we've had a good go now explaining why we had a bright spot in the middle. Why we're now going to attempt to explain why is it dark? Why is there no wave activity at this point? And I'm going to risk using ink to shape again, although I may regret it. So the theory is if I draw a line here and it thinks it's an arrow, yeah, I get a straight line. That's not too bad. It doesn't interpret anything other than arrow. It won't. I think we'll just have to do our best to patch that arrow up, even though it's the wrong length. What's obvious now is that these waves here, the waves coming down here, have travelled further than the waves travelling along here. How much further have they travelled? Well, it's forming a dark spot. It's the first dark spot off centre. And therefore, we must have destructive interference. So going back to, I really don't want to open my emails at the moment. Right, good, that's gone. So going back to this diagram here, to have a path difference, to get destructive interference, we need a path difference of half a wavelength. So back to this picture here, we can say that here the path difference is half a wavelength. That arrow there is half a wavelength longer than that arrow there, leading to destructive interference. Whereas here, the path difference was equal to 0 because both sets of waves had travelled the same distance. Let's just colour code those a bit. So we'll use red for bright. So we've got bright here, bright here, bright here, bright here. All the way along that line, we've got strong wave activity. Whereas all the way along this line here, we've got low or no wave activity. So let's now write in what the path differences must be. Here we're back in phase, but clearly they've not travelled the same distance. So here we say the path difference is a wavelength, leading to constructive interference. Here where it's dark again, the path difference is 3 over 2 wavelengths, 1.5 wavelengths. Here where it's bright again, it's 2 wavelengths. So this pattern is entirely formed by superposition, the waves from the two sources meeting. Where they meet in phase, we have a bright spot, and where they meet in phase, the path difference is a whole number of wavelengths, 1 wavelength, 2 wavelengths, 3 wavelengths. Where it's dark, the waves are out of phase, and the path difference is a half wavelength, 1.5 wavelengths, 2.5 wavelengths, or half, 3 over 2 lambda, 5 over 2 lambda. Let's just go back to the animation. I think we'll just put it into 3D again briefly. So again, you've got to imagine there are two sets of waves here. It looks just like one. All along here, down that center line, the waves meet, peak meets peak, crest makes crest, and we get strong constructive interference. Along this line here, hopefully you can see my cursor just fine, destructive interference because the path difference is half a wavelength. And we'll just end on here just by realizing that actually if I make that into 2 slits, if I just rotate these, see if I can simulate what I'm talking about. Spent ages planning this, and then you think suddenly you have a good idea, but you hope it's a good idea. Yeah, so we can imagine we've got a point here where the two sets of waves, because they're rotated similar amounts, have arrived in phase because the path difference was was 0. They've both travelled the same distance. So I'm now going to rotate that one so it's pointing up in this direction. I'm going to rotate this one. What I need to happen is, yeah, I think we've done it, is that if we imagine, let's go back to the pen tool. This point here, you can see a trough of this wave is meeting the peak of that wave, and that would lead to destructive interference at that point, so we'd get a dark point. So it's the changing nature of these two patterns of waves that leads to the pattern. And we'll get you to do some practice now explaining how these fringes arrive through constructive and destructive superposition.